Alright, so this video covers displaying quantitative data. We've already done a lot of examples in the previous video talking about displaying categorical data. This one is specifically for quantitative data. Alright, so quantitative data. Remember, quantitative data is numerical values. So how many goals did you score? What's the gas mileage of your car? What is the sum of rolling two die? How many people live in your house? How many shoes do you own? What's your IQ score? The answer to all of those questions is a number with a unit. Even if that unit is I scored 3 goals versus I have a height of 6 centimeters, whatever. You have to have a number with a unit. That makes it quantitative. So the first way that you could display quantitative data is what we call dot plot. Dot plot is probably one of the simplest, easiest ways. Typically, we use a dot plot though if the values come in the form of whole numbers. You don't have to, but it's typical. Each dot represents a result. So how many goals did we score each game of the season? Well, you could see that one game we scored 0 goals, one game we scored 14, one game we scored 13, and then several games we scored 4. And notice how, since it happened multiple times, we just stack the dots on top of each other. So a dot plot is probably one of the most common and very easy ways to see how the data is broken down. A dot plot allows us to see where most of this data falls. So we realize we scored most of the time we scored 2, 3, or 4 goals. And then there's this huge gap, and in a few extreme circumstances, we scored 13 or 14 goals. Now, when we examine quantitative data, we want to talk about a couple things. We want to talk about the shape of the data, the center of the data, the spread of the data, and if there's any outliers. So we have to remember to talk about those 4 things. Those are the 4 most important things that you have to talk about anytime the question says, describe what you see in this quantitative data display. Alright, so here's an example, another dot plot of gas mileage. So we looked at 24 cars made in 2012, and we looked at the gas mileage. Remember, gas mileage is how many miles the car gets per gallon of gas. So if I were to show you this graph and I said to describe it, we have to make sure we mention shape, center, spread, and any outliers. So the shape is just talking about, well, the shape of the dots. What do they kind of form? So I'd say something like this. The data is peaked around 30 miles per gallon, and there's a main cluster from 23 to 34, but there are some gaps from 18 to 23 and 40 to 48. So basically, when you're talking about shape, you're just kind of describing what you see. Where's most of the data fall? Where are some gaps and things like that? Center, you're just trying to give a typical value. So what is a typical, or what do you think is the most typical value that would represent all the cars? So in this case, I would say somewhere right around the middle. Somewhere right around the middle looks like maybe around, right around here, somewhere around 28 miles per gallon. Summarizes, yes, some cars are more and some cars are less, but we're just looking for one number that kind of represents the center. The spread. The spread of the data is just talking about where the data goes to and where it comes from. So the data is fairly spread out. It ranges all the way from 18 to 48 miles per gallon. That's a pretty big spread. But again, I do see that most of the data is clumped or clustered from 25 to 30. So again, I'm just writing a couple things about how the data is spread out. Outliers. It appears that the cars have outliers around 18, 40, and 48. Now again, what's an outlier? Well, right now we're not going to be extremely descriptive of that, but basically an outlier is a value that looks way far away from everybody else. And this 18 down here, and this 40, and this 48 definitely appear to be outliers. Okay, let's talk a little bit more about shape because I don't want it to be confusing. At this point, a lot of kids say, I don't know what to write. I don't know what to talk about. And that's what I'm going to try to give you right now in these slides. There are a few common shapes that data can take on, and we should discuss them. The first is symmetric. Symmetric shape means that the left side and the right side of the graphs appear to be approximately the same. So if we have a symmetric graph, we basically have a graph where we see data on the left side starts to mirror data on the right side. So we see low on the left, low on the right, high in the middle. Another symmetric data could look like this, where we see data that if you were to throw a mirror down the center, you would mirror side to side. Symmetric. I'm sure most of you get what that means. Now, skewed is where one side of the data has more data than the other. So skewed to the right is more data on the left and less on the right. So skewed data would look something like this. So there's more data on the left, so a lot of dots on the left, and then as we move to the right, there's less and less dots. So we see more data on the left, less data on the right. We call that skewed right. Skewed left is the opposite, where most of the data is on the right-hand side, maybe towards higher numbers, and on the left-hand side is there's less data, less dots. That would be skewed left. Let's look at some nice pictures of this. Here's a dot plot that is very, very symmetric. Now, is it perfectly symmetric? No. In the real world, you're very rarely going to see perfect data. But here's what we did in this picture. We rolled 2 die. And we rolled 2 die, and we added up the 2 values that were facing up. And here's the outcome. So twice did we roll a sum of 2, right? That's called snake eyes. So down here we see twice we rolled a sum of 2. Maybe 5 times it looks like we rolled a sum of 12. And most of the time we rolled a 6, a 7, or 8. Those kind of came up the most, and there's a big clunk there in the middle. But we see this nice and symmetric, right? A little bit data on the left, most of the data in the middle, a little bit data on the right. That would be considered symmetric. Here's 2 datas that are skewed to the right and skewed to the left. On the left-hand side here, we have test scores. We see that most students scored 85 or higher, right? So most students were in this 85 or higher range. There's a bulk of the data on this right-hand side, but there were a few scores over here on the left, hence the skewed left. We call this a tail, right? So we have the bulk of the data here, and then it tails off to the left. So when the data tails off to the left, we call it tailed left or skewed left. Here's another example of, hey, how many siblings do you have? A couple of kids said they have no siblings. A lot said 1 and 2. Very few at these higher values of 5 and 6. So again, most of the data is on the left, and then it kind of starts to tail off to the right. That is skewed right. So we kind of talk about the direction of that tail. So if the tail goes to the right, skewed right. Tail goes to the left, skewed left. All right, another way to talk about the shape is to talk about where most of the data falls. So we call data unimodal if one bin kind of has clearly the most data. So once again, if we look at this dice example, we see that right in the center at 7 clearly had the most. Most of the rules had a sum of 7. It is single peaked. So we see this one peak right here in the middle. We call that unimodal. Here's another example with our test scores, right? We see this one peak right here at 90. So there's one giant peak. Most students got a 90% on the test. We see that one peak. That's, again, unimodal. Down here with siblings, again, we see this one peak here, right? The large majority of students only had one sibling. That would, again, be unimodal or single peaked. We also have bimodal. Okay, here's an example of bimodal, where we see 2 kind of major clumps of data, both kind of sticking up. Now, notice that they're not exactly the same heights, but that's okay. So on this left side here, we see this one hump of data in the middle, maybe somewhere around 1.9, where there seems to be a lot of data. And then we got this other hump over here, where there's a lot of data around 4.5. Now, notice the 1.9 is definitely lower than the 4.5 in terms of how many dots are there, but we definitely see 2 clear peaks, right? 2 mountaintops. Not identical, but 2 mountaintops. That's where we get this term bimodal from. All right, uniform is another term where we see all the data is about even, right? So here's an example where the data doesn't really change a whole lot from 1 to 10, right? So about the same number of people had a score of 1 as the people that had a score of 10. Yeah, there were a couple more people in 3 and 6 maybe, but it was kind of uniform throughout. There wasn't a really big discrepancy throughout the data. That's where we get the term uniform from. All right, now, oftentimes you're going to be shown 2 data displays, and you have to compare them. So basically, when you compare 2 distributions, you compare their shapes, you compare their centers, you compare their spreads, and you compare their outliers. Now, hopefully you guys know what the word compare means. Compare doesn't mean talk, 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 and then talk, talk, talk. It means talk about the 2 things together at the same time as you compare them. Here's an example. Okay, these are the number of people that live in houses in South Africa and the United Kingdom. Let's compare these 2 dot plots. Well, what are some things I notice in terms of the center? Well, I notice for South Africa, it appears the center is somewhere probably around, it definitely looks skewed to the right. Do you see that? And most of the data is on the left, a little bit of data on the right. So I definitely want to call this one skewed right. But I'd also mention the center. The center is probably, because it's skewed, I mean, it looks like most people are right here at 4, but because it's skewed, the center is going to get pulled to the right a little bit. So maybe around 6. So it looks like maybe around 6 people is what's pretty typical in terms of how many people live in a house. Whereas in the United Kingdom, it's a little bit more symmetric. Okay, it's not so skewed. I see a little bit lower on the left, and it's kind of lower on the right, and then most in the middle. That's a sign of symmetric, and it looks like the center's around 4. So it does appear in South Africa more people live in each house than in the United Kingdom, 6 versus 4. So I'm comparing their shape, skewed right, versus symmetric. I'm comparing their centers. Now let's talk about their spread. South Africa is clearly more spread out. They go all the way from a low of around 3 people to a high of 26 people. That's a big spread. The data is clearly spread out. Where in the United Kingdom, the data is very clustered together, looking like between 2 and 6 people. So it's very tightly compact and very, very much clustered there. Lastly, outliers. In terms of the United Kingdom, I don't really see a ton of outliers. In fact, I don't really see any. It looks like all the data is definitely clumped from 2 to 6. Whereas in South Africa, I definitely see some extremes here. I see this 26. I see this 15. There were a couple households that definitely had a large number of people living in them. So when you see 2 dot plots, you want to make sure you can compare them by talking about center, shape, spread, and outliers. All right, another way to display quantitative data is with what we call a stem plot. This display is used for fairly small sets of data. They give a quick display of the data, and more importantly, they include the actual numerical values. This is really important. All right, so here's an example of a stem plot. So we asked 20 girls, hey, how many shoes do you own? One girl told us 50 shoes, one girl told us 26, another told us 26. So this again, how many shoes do you own? So when we make a stem plot, the first thing we have to do is choose our stems, which is going to be our tens digit. So we had somebody in the 10s, 20s, 30s, 40s, 50s. That's what these numbers here represent. Then now the single digits represent the leaves. So for example, this girl that had 50, that's the 0 in the 5. So I'm going to put the 0 right here in that 5 column. 26 would be a 6 in the 20s column. Another 26 would be that 6 right there. 31 would be a 1 in the 3 column, and so forth. Now the important thing you have to do in a stem plot is when you're all done, you want to make sure that they go in order. So once I'm done putting all these values in here, I want to make sure that I have them in order. So for the 50s, I want 0, 0, 1, 7. 9 for the 40s is pretty easy. 0, 1, 4, 8, 2, 3, 3, 4, 6, 6, 3, 3, 3, 5, 9. Just make sure that everything's in order. So it's a nice way to display the data. Now you also want to make sure with any stem plot you have a key. That way you can explain what these numbers represent. Without a key, I mean, this 1, 3 could be 1.3, it could be 13, it could be 1,300, it could be 130. So you need to have a key that shows, oh, a 4/9 means 49 pairs of shoes. All right, well, what about men, right? Men will have shoes too. So we have 20 males, and we asked them how many shoes they own. And here's the results. So once again, I made a stem plot over here with 0, 1, 2, and 3. And then I put the numbers in here. There's the 4, the 5, the 5, the 5, the 6, the 7. You get the idea. They are in order. So one thing I noticed is that men typically have less shoes than women. Now, we can also do something what's called a split stems plot, okay? And here is if we want to just kind of break up the data a little bit. Basically, we take the zeros, which are the single digits, and we break it up to 2 zeros. Now, this first 0 is for 0 through 4, and this next one is 5 through 9. So this is 0, 1, 2, 3, 4. This is 5, 6, 7, 8, 9. So it just kind of splits the data up. Same thing, the 1, 1, this is for 10 through 14, and this one would be 15 through 19. 20 through 24, 25 through 29, you get the point. So now all of a sudden it just separates the data a little bit here. So this 4 would go right here, and then we got 5, 5, 6, and they're all going to kind of pile up there. And then it just basically spreads the data out a little bit. Sometimes it's a little bit easier to read. Not that there's anything wrong with this first one, it's just another way that you may see a stem plot created. Okay, we also have what's called a back-to-back stem plot. A back-to-back stem plot is a great way to compare two groups. So again, this is my data for how many shoes you own. I did do a split stem, so I see the 0, 0, 1, 1, 2, 2, 3, 3. And then I did males on the left, females on the left, males on the right. And this is a really nice way that allows me to compare the data. Okay, so I can clearly see that typically females own more shoes. Looks like females might have some outliers around 57. See, I read that wrong. That'd be 57, 50, and 51. Males typically are around, the typical center for the males is probably around 6 or 7 pairs of shoes, whereas for the females it's probably somewhere around 26 pairs of shoes. So again, females clearly have more. Females are also very, very more spread. They're spread all the way from 13 to 57, where males are kind of spread from 4 to 38, so not quite as big as a spread. And then I could also look at shape, right? Males definitely probably looks a little bit skewed right. Most of the data is down here on the bottom, and a little bit of data is at the top. Where the females, you could maybe even say symmetric for the females. It's really not like a huge skew. I don't really see one. I see a lot of data in the beginning, the middle, and the end for the females there. Okay, the last way that you can display quantitative data is with what we call a histogram. Now, a histogram looks, smells, tastes, everything about a histogram looks like a bar graph, but it's not. You have to remember this is an important part of statistics. Bar graphs are very, very specific for categorical data. Histograms are basically bar graphs, but for quantitative data, but they have a special name called a histogram. Guaranteed you've seen these before, you've probably just never heard them been called histograms. So, quantitative values can often take on many values. If we group some of these values together, it can be easier to see shape, center, and spread. So the most common way to display quantitative data is a histogram. This is the most common. So, how do you make a histogram? Well, I'm going to walk you through it step by step here. First, you want to organize your data into groups or bins based on the intervals you establish. I'll show you what I mean by this shortly. Then you want to find the counts of data that fall into each bin. Then you want to actually make your graph by labeling your x-axis based on the intervals that you set up in part 1. And then step 4 is you actually want to make bars that show how much data falls into each bin. So, here's an example to make this very, very clear. What percent of people in each state are foreign born? For example, in Alabama, 2.8% of the population was born outside the United States, whereas some other countries have a lot higher. For example, California has 27.1% of the population born outside. This is a lot of data, a lot of big and different numbers, so I really want to find a way to organize it nicely. The first way is to create a frequency table. Basically, I make my bins here. This first bin is 0 to 5. Then 5 to 10. So basically my bins are of size 5. You can choose the bin size. It's completely up to you. But make sure you understand that these bins are what we call left-handed, which means you're equal to the left number and you go up to the right number. So this first bin goes technically from 0 to 4.999999999. This bin right here goes from 15 equaling 15 all the way up to 19.9999999. So make sure we call them left-handed bins. Then you actually want to go back to your data and count how many, in this case, how many states fall into each bin. So I'm going to go back to my previous data and I'm going to count how many bins are 0 to 4.9999, basically 0 to 5. And then that is what's going to go here. So I counted 20 states that were from 0 to 5%. 13 states were from 5 to 10%. Again, technically 5 to 9.9999. 9 states I counted from 10 to 15. 5 states 15 to 20. 2 states 20 to 25. In 1 state that was 25 to 30. Then you can make your histogram. So notice the x-axis down here. The x-axis has the bins that I set up, 0 to 5, to 10, to 15, to 20, to 25, to 30. Those bins have to always be equal in size. You can't just jump around 0 to 5, to 17, to 22. You've got to stay consistent. And then up on the left-hand side is basically how many states you counted in each bin. So if you recall from the previous slide, there were 20 states from 0 to 5, so I'm going to make that bar go up to 20. There were 13 states that were from 5 to 10%, and then I made that bin go up to 13, and so forth. So it really gives you a nice picture of where the data falls. We could also have an example of what we call a relative histogram. A relative histogram, we talked in class that the word relative means percent. So instead of showing the number of states in each bin, it shows the percent. So if you recall, there were 20 states in that first bin. So 20 divided by 50 states is 40%. There were 13 out of the 50 states from 5 to 10%, so that would be 26% of the states. And then you build your histogram not based on how many people, or I'm sorry, not based on how many states, but the percent of the states. Notice between the two histograms, they look identical. And you should see very similar looking. It's just a matter of where your bins go to, whether it be a number or a percent. Don't forget, you always have to describe what you see, right? So let's mention shape, center, spread, and outliers. Clearly skewed to the right, right? I got a ton of data on the left-hand side, and as I move to the right, there's less and less data. So most data is on the left-hand side from 0 to 10. Less data on the right, hence skewed right. Center. The middle falls approximately between 5 and 10%. It looks like somewhere right around here would be the middle of the data. It looks like most states have 5 to 10% foreign-born residents. The spread, well, the spread is pretty simple. It looks like it's spread somewhere from 0, or about 5 to 25% is where the bulk of the data is spread out between. Outliers, although there were a couple high values here, I don't know if I would necessarily see any state that is way outside of the pattern. Again, there's not as many from 25 to 30 as there is from 0 to 5 and 5 to 10, but I don't see any state that's way far off, so I don't know if there's necessarily any major outliers. All right, let's talk about how you could change bin size. So understand that the bin size is completely up to you. On the left-hand side, I changed the bin from 0 to 5, and then I did 0 to 2.5. So what I did was I kind of broke it down a little bit more, and that just created more bars or more bins. So this mark right here would be 2.5, which means that this bar right here is how many states are from 0 to 2.4999999% of foreign-born people. So that's where these is. So just understand that you get to pick the bin size, and it just kind of, I mean, we still see the data is skewed right, correct? I mean, it still looks very similar. We still see a bulk of people around that 5% mark. It's just a different way to change your histogram. So we're going to learn in class about making histogram on your calculator, so don't worry about too much about copying this down now. We'll talk about that in class. But the key idea is that you know that there are several different ways to display quantitative data. We got a dot plot, we got a stem and leaf plot, and we have a histogram. Those are the three most common. And then anytime we see one of these graphs, we want to talk about the graphs by mentioning their shape, their center, their spread, and the presence of outliers. All right? We'll finish the rest. We'll do some activities in class. Hope you enjoyed the video.